Yeah, so good evening, everyone. So today we are in the week 11 problem solving session of the NPTEL course NMR Spectroscopy for Chemists and Biologists. So I will wait for a few minutes and then I will start today's session. So in the last lecture, we were discussing about two-dimensional correlation spectroscopy experiment and the general scheme of a multidimensional NMR spectroscopy. Uh, we had looked into 2D COSY and J-resolved COSY experiments. So today what we will do is we will continue our discussion further and we will understand three main concepts today. Uh, those are two-dimensional COSY. A part of it was left in the last week. So I will discuss that part and a few questions that may be asked in your exam as well as they were also in the assignments. So we will try to look at these concepts in detail so that if you have any doubts in these sections, they are cleared if you go through this lecture. And then we will also look into NOSY experiment, nuclear Overhauser spectroscopy, FX spectroscopy, and DQF OZ. Okay, that is double quantum filtered COSY experiments. Okay. So there are a couple of questions that were asked in the assignments. So you need to understand these concepts in detail. So I will wait for another 2 to 3 minutes for other learners to join, and then I will start with today's session. So I hope all of you are going through the lectures and trying to solve the assignments. Soon you will be having your exams on for this course. So you need to clear all the concepts. Okay, so we can start now. Okay, so I will share the slides for today's class. So I hope the slides are visible. Okay, so yeah, hello everyone. I'm Akash Jyoti Pathak. I'm a PMRFTA for this course NMR Spectroscopy for Chemists and Biologists. And today we will be dealing with the week 11 problem solving session for this course. I'm a PhD scholar here in the Department of Biosciences and Bioengineering at IIT Bombay. And I am working in an NMR spectroscopy lab. So let's start today's session. Yeah. So I hope you remember what we were discussing in the last session. So we were mainly talking about the, just a second. Yeah, so we were discussing about the correlation spectroscopy experiment. Okay, so in the two-dimensional correlation spectroscopy experiment, the basic pulse sequence that is followed is we first we provide a 90-degree X pulse. Okay, 90-degree X pulse. Then there is a T1 time period, which is also called the evolution period. Then there is another, give me a second. Then there is another 90-degree X pulse. This is followed by the T2 period. Okay, T2 period also known as the detection period. Okay, so in the T2 period, the FID is collected, right? The FID is collected, the free induction decay is collected during the T2 period. So this is the general scheme of any multidimensional NMR spectroscopy experiment. We had seen into, looked into or understood what is, how the segmentation of time axis takes place in a multidimensional NMR spectroscopy experiment. And so the same is followed here in this 2D cozy experiment. So so this was the basic pulse sequence, and then what we had seen is that we obtain two time points T1 and T2, and these time points are then Fourier transformed. And on Fourier transformation, what do we get? So the signal that is collected is T1, and we get two time points T1. It is called the dependent time, and this is called the independent time, right? So after Fourier transformation of this, we get the time domain is converted into the frequency domain, F1 and F2, right? F1 and F2, and then this is what we, in a 2D cozy spectra, what do we see? So we have two dimensions. One is the F1 dimension and another is the F2 dimension. The F1 dimension is present on this axis, y-axis, and this is on the x-axis. And what we observe, so what is the general structure of a 2D correlation spectroscopy of this spectra? What is the general structure? So we get diagonal peaks. Okay, so this is the diagonal. So in the diagonal we have, give me a second. Okay, yeah. So we get two peaks, two different peaks. One is the peaks that we observe in the diagonal of this spectra. Those are called the diagonal peaks. Okay, the diagonal peaks. So these are, and then there are off-diagonal peaks, or they are also called the cross peaks. Okay, so the diagonal peaks, we had solved questions on what is the peak pattern or the fine structures that are observed in the diagonal peaks of a 2D cozy. So the diagonal peaks in a 2D cozy have dispersive line shapes, and they have a positive sign, and the off diagonal peaks have. So this we will look into detail today, but I'm just giving you an overview. So the off diagonal elements, or the cross peaks, they have absorptive line shape. Absorptive line shape means what? We will have this kind of a shape. This this shape is called an absorptive line shape. Okay, or it can be like this also. And dispersive line shape means we will have somewhat like this. So these peaks will be so there will be an upper peak and a positive peak and a negative peak in the dispersive peaks. So how does the shape looks like? We will talk about this. Yes, again. Okay. So that is so this is the F1 dimension, and this is the F2 dimension. What the information carrier? The information carrier is present in the off diagonal elements, or the cross peaks carry the information, and we had seen that we will get cross peaks when one spin is J coupled to another spin, right? So if there is a spin say A and another spin say B. So if the A nuclei is coupled to the B nuclei, then we will observe and here also we will have what? A and B. Okay. A nuclei and B nuclei. Okay, and so the diagonal peaks does not give us the information whether a nuclear spin is coupled to another nuclear spin, but this cross peaks. If we get a cross peak, if then we can say that that cross peak is coming because the A spin is coupled to the B spin by J coupling. Okay, so in this one also. So that was the basic concept. Okay, so now what we will do, what are the fine structures that are observed in the diagonal peaks in a 2D cozy? So we had derived all these expressions, so uh, I will not go into too much detail. So these were labeled as 1, 2, 3, 4, right? So they were labeled in this form. This is the 5. Okay, and after the fifth time point, the density operator or the product operator, we get this expression. Okay, and then for we get the observable. We will get the observable when if we take the trace of this rho 5d dash I ky. So the trace of this rho 5d dash I ky on solving this, we will get this equation, right? And if we split this into, and if we solve this further, if we apply those trigonometric formula, and we break it down, then we find that we get 4 different terms, right? We get 4 different times: sine omega k plus pi j k l t2 plus sine omega k minus pi j k l t2. And then this is the first term, this is the second term, third term, and fourth term. So what we can, so if you observe this equation very carefully, you will see that all these are sine terms, right? All these are sine terms, and you have 4 different terms. So these 4 different terms will lead to 4 different peaks. So that is what I was explaining previously, that if you look at the fine structures that are observed in the diagonal peak of a 2D cozy, you will see there are 4 different peaks. Okay, so the 4 different peaks are so these 4 terms will result in 4 different peaks in the diagonal in the diagonal elements. Okay, so the sign. Now, why have I indicated this plus 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 plus? So if you see these terms, they are all plus they're all that they have all positive sign. They have all positive signs, right? So that is why these are this is indicated in this form plus 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 plus. And now also in the T1 dimension, in the F1 dimension, you will observe a peak at this point, nu k plus. So what has been done here is basically omega k, you can write it as 2 pi nu k, right? 2 pi nu k, and this two then and this you can write it as, so omega k, you can write it as 2 pi nu k plus jkl. And then you can take 2 pi common. You can take this outside the bracket and then you can write it in this form, nu k plus jkl by 2. And similarly here also the same thing can be done. The omega k can be replaced as 2 pi nu k minus pi jkl. So once you take the 2 pi outside this bracket, you will get this expression. Okay, so this is what you will get in the F1 dimension, right? This is what you will get in the F1 dimension. So at this point, you will get this peak. Then at nu k plus jkl by 2, you will observe the second peak. Okay. You will observe the second peak. No, you will observe this in the F2 dimension at this point, nu k plus jkl by 2. Similarly, for so these ones. So these are, so at which point you will get these peaks. Those are those you will get this from this value, nu k plus jkl by 2. You will get one peak. And if in the F2 dimension, what is the position? It is nu k plus jkl by 2 at this position. So you will have a peak over here. Then in the second, moving to the second second term. So if you move to the second term, you will see that nu k plus jkl by 2. So this one, nu k plus, so this one, nu k plus jkl by 2 and nu k minus jkl by 2, you will have this second peak. And then this third peak, and this is the third peak, and this is the fourth peak. So so why is it dispersive? So if you see that all these are sine functions, so a sine function always gives us dispersive line shape. Okay, so you remember that what you have to understand here is that the fine peaks fine peaks in a other, my eraser is not working today. So the fine structure observed in the diagonal peaks of a 2D cozy experiment has positive dispersive line shapes. Okay, so in the next slide, we will look how this dispersive line shape looks like. And this was also there in your discussed in great detail in the lectures also. So this is the take-home message from this slide. So the fine peaks that we observed, or the fine structures that we observed in the diagonal peaks of a 2D cozy spectra has dispersive line shapes, and they have positive character. Okay. So remember that why does it have dispersive line shape? Because they're all sine functions. And from where do we get this sign? So if you solve this, the trace of this density operator, then you see that all these are positive signs, right? All these terms have positive signs. So that is what is shown over here. Okay, so yeah, this is how the fine structures in the diagonal peak of a 2D cozy looks like. So yeah, so this axis has F1 on this is, if you consider this as y-axis, this has F1 dimension is on this vertical line, and this F2 axis is on this horizontal line. And so you have two spins. So if you have two pins, K and L, both have I equal to half. So each of these spins will produce a characteristic spectra at their respective frequency, right? So you see disperse. So what is this? This is basically a contour map of the frequency that you will observe. So basically you have the spectra, but you have cut it and you are observing it from the top at different layers. And so that is how the fine structure in the diagonal peak fine structures in the diagonal peak of a 2D spectra look like. So they are all positive and dispersive line shape. Yeah, so this is what I was explaining, that the diagonal peaks in a 2D cozy have in-phase dispersive line shapes along both F1 and F2 frequency axis. Okay. So they have in-phase dispersive line shapes. Okay. So why do they have in-phase? So you had seen while we were solving the using the product operator formalism, we were solving the density operator at different time points, rho 1, rho 2, and then we had obtained different expressions, right, to yk. So based on that, that gives us in-phase dispersive line shapes. Okay, so okay, based on this concept, try to answer this question. So in a cozy spectrum, the fine structures in the diagonal peak have, so there are four options: anti-phase absorptive components, in-phase absorptive components, in-phase dispersive components, and anti-phase dispersive components. Okay. So just now we discussed that in a cozy spectrum, how will the fine structures in the diagonal peak look like? So they are all sign terms indicating that they will be what? They will be, they are dispersive components and they have in phase character, right? Yeah. So we discussed just now that they have in phase dispersive components. So we have four terms. We get four terms when we after the FID is collected and we Fourier transform it. Then on Fourier transforming it, when we solve the trace, or when we solve this trace of this rho 5D, we get four terms. So all these four terms will give us four different peaks in the diagonal part of the 2D spectra. And so these four peaks, they are all sign components, and we will have in-phase dispersive components. Okay. Yes. So the correct answer is in-phase dispersive component. Okay. So direct questions like this can, so these are direct questions, and if you have to just understand the concept. So the diagonal peaks and what will be the fine structures that will be present in the diagonal peaks. So these are direct questions. Then this is another question. In a generalized 2D experiment, preparation, evolution, mixing time is collected along T2 axis explicitly. Data is collected along both T1 and T2 axis explicitly. Data is collected along T1 axis only. Data is collected alternatively along T1 and T2 axis. So this concept, the generalized 2D experiments, we had discussed in the last live session. Okay. So if you remember the concept, you can try to answer this question. So we had seen that how does a generalized 2D experiment look like? So there is a preparation time where you give different pulse sequences, preparation period, then this is followed by an evolution time. During the evolution, so during the preparation period, what happens? The transverse xy magnetization is created. So you apply 90-degree pulses along axis, and depending on that, xy transverse magnetization be created. Then in the T1 period, this is called the evolution period. Then following this, there will be a mixing period, right? There will be a mixing period, and then there will be detection period. Okay, wherein the also called the T2 period. T2 period wherein the DFID will be collected, right? So So the main signal that is collected is in the T2 period, right? That is why this is also called the detection period. This is also called the detection period. And in the evolution period, this is also called the T1 period. We allow the different spins. There will be relaxation and different. Uh, once the transverse magnetization is created, then the spins will relax during this period and it will be allowed to evolve. And then in the mixing period, there will be transfer of magnetization between the spins. If there is dipolar coupling, J coupling, all these things will happen, right? So the main data is collected in the T2 period, in the detection period. Okay. So I told you the answer. So based on this, what will be the correct option? T2, the T2 time period is also called the acquisition period, right? Where the data is collected. The actual data is collected in the T2 period of the acquisition period. And the on Fourier transformation, we will observe that 2D Cosy spectra that I was showing you in the previous slide. Yeah, so the correct answer is option A. Okay, so option A, the T2 axis explicitly. Data is not collected along, so the second option, data is collected along both T1 and T2 axis explicitly. This is wrong. Data is not collected along the T1 axis. Okay, so the information that is there in the T1 in the that is we collect the information that is present in the T1 axis, that is Fourier transform to get two different dimensions, F1 and F2 dimension. Okay, so what is after this transverse magnetization, what is happening? That information is collected, but the data is collected only during the T2 period. Okay. Yeah. So so look at the solution. Though there's a detailed solution. It says that in a generalized 2D experiment, there is segmentation of the time axis, right? We had seen what is segmentation of the time axis. So the first is the preparation period, followed by the evolution period, also called the T1 period. Then there is a mixing period. Then following the mixing period, there is this T2 period. In the T2 period, the FIDs are collected with increments of T1 period. So that there is we have seen T1 to T1 to 3T1. So with each increments of the T1 period, what is the how is the FID changing that we collect, right? That we collect, and the intensities at these points are then plotted get this to get the spectra. The 2D data body T1 to T2 is Fourier transform to generate a 2D spectrum called as the F1 and F2. Okay, so this F1 is on this axis, the F1 axis, and this is the F2 axis. Okay, we have two frequency axes. One is called the F1 axis and one is called the F2 axis. Now try to answer this question in a multipulse experiment. The selection of pathway should end in Z magnetization, single quantum coherence, double quantum coherence, zero quantum coherence. So these different coherences. So we in your earlier lectures you had learned about this concept that the that for the transitions of the spin, the selection rule, we follow a selection rule. The selection rule is that the difference in this magnetic quantum number, if the difference in magnetic quantum number is plus minus one, in only such cases the transitions will take place. So for moving from one state to another state, right? So only those transitions are possible where the del M is equal to plus minus one, right? And so on the basis of this, there are different kind of quantum coherences. So, yes, again, yeah. So we had seen this, there can be, so if there is a two spin system, for a two spin system, for example, EB spin system, you can have four possible transitions, right? You can have four possible states: alpha alpha, alpha beta, beta alpha, and beta beta, right? You can have four different states: alpha alpha, alpha beta, beta alpha, and beta beta. So this is the M equal to plus 1, this is m equal to 0, and this is m equal to -1 state. This state is the m equal to -1 state. So which transitions are possible? Alpha alpha to beta alpha, alpha alpha to alpha beta, then alpha beta to beta beta, beta alpha to beta beta. So these are called the single quantum transitions. These are called the single quantum transitions. Why? Because for each of these cases, you see that the difference in magnetic quantum number is 1, right? So 0 to -1. So there is a -1 change, and then +1 to 0. There is also a +1 change, right? So these are called the single quantum transitions, single quantum transition. But other than these, two other transitions take place, but they are not observable. Okay, so this is so one transition is from this beta alpha to alpha beta. So this is also m equal to 0 state. This is also m equal to 0 state. So that is why if there is a transition of the spin from this beta alpha to alpha beta, then we call this as, what do we call it? We call it zero quantum transition. Just give me a second. I will connect the charger. Yeah. So what was I discussing? Yeah, so I was discussing about the different transitions that can take place. The single quantum transitions, that is when this spins move from this, they are indicated in this form, right? From this m equal to +1 to m equal to 0 state, these are called the single quantum transitions because there is a change of +1 or -1. But the transitions that take place from alpha beta to beta alpha, so both these are in m equal to 0 state. So that is why these are called the zero quantum transitions. Zero quantum transitions. Then another transition that is possible is that alpha alpha can move to the beta beta state. Okay. So if alpha alpha is moving to the beta beta state, then if you calculate the del m, what will you get? You will get 1 minus minus 1. So there is a change of 2. So there is a change of 2. So if the alpha alpha state moves to the beta beta state, then that is called double quantum transitions. So all these different transitions, all these different terms that we had derived this when we were solving this density operator expression. So these double quantum transition and zero quantum transitions, they all take place um, in the evolution period. In the evolution period, but the only observable that is that we can observe those transitions are of the observable terms are the single quantum transitions. Okay. So now in a multiples experiment, the selection of pathways should end in. So there was for detecting the signal, the pathway that we follow, that is this, there is this preparation period, then evolution period, then mixing period, then T2, then in the T2 period, we are detecting the signal that should end in which type of coherence for detecting the signal that has been asked in this question. Okay, so that will be what? try to answer this question. So that will be obviously what I said, that the single quantum coherence is the observable, it can be detected. So that is why the answer for this question is single quantum coherence. Okay, so the transitions, so this is I have explained here, the transitions where del m equal to plus minus 1 are called single quantums. All transitions where del m equal to plus minus 1 are called the single quantum coherence. The double quantum coherence is not directly observable, but they are created in the course of pathway magnetization flow. So that is what I was explaining, that in this evolution period, all these different they are these double quantum transitions and zero quantum transitions. These are created during this flow of magnetization, but they are not directly observable. So when a detector is put, they are not directly observable, and hence they have to be converted into single quantum coherence for detection. So this rule, this del m equal to plus minus 1, this is called the selection rule. Okay. I hope this is clear. Okay. So there were preparation period, and then this is a 90-degree expulse, and then there are different times. So these T1, T2, T3. So in all these terms, there will be flow of magnetization, and magnetization flow will take place. And during this flow of magnetization, these different terms are created. Okay. So which terms are correspond to this single quantum coherences, which correspond to the double quantum coherences, which are the zero quantum coherences. So these I had when we were deriving the this with 2D cozy, the information that is present at different time points, row 1, row 2, row 3, row 4, we had solved this, right? So during these points, even you had found different terms that were coming, like 2K, IX, ILY. Then there were different terms like 2K, 2I, K, Z, I, L, Y. So these different terms. So these some of these terms correspond to the zero quantum coherences, some correspond to double quantum coherences. So we will look into this in more detail in the next slide. So in the multi-pulse 2D experiment, which of the terms are observable? So just now we discussed that the only terms that are observable are the terms that arise because of single quantum coherences. Okay, so now you have to identify that all these terms we had obtained in this different density operator time points, right? Time row 1, row 2, these terms. So if you go through the last lecture uh, and see the lecture, pause the lecture, then you will find these terms. I had derived this. So which of these terms will be observable? So what do these different terms indicate? So IKX, what does this mean? So IKX means magnetization of K spin along the x-axis, right? Magnetization of spin K. IKX means magnetization of spin K along the x-axis, along the x-axis. Or you can also write it in this form, X magnetization of spin K. This is X magnetization of spin K. Similarly, IKY. What does the IKY mean? It is Y magnetization. Y magnetization of, actually, there is an error in this in the format in which this is written. So this will be IKX. So this K will be in in subscript. Okay, this will be in subscript. I will correct this uh, in the slides. So ILY. Okay. So yeah, IKY, what does it mean? It means that Y magnetization of spin K. Y magnetization of spin K, then IKZ is Z magnetization of spin K. Okay. So these are the different terms. So these are the different definitions because so these terms are they often come when we derive this expression. So now, which terms are observable? So, remember that always this IKX, this term is only observable because this is the term that correspond to single quantum coherences. The other terms that are produced, they are all, yeah, this like this 2 IKX, ILY. So this has both, say, this has both zero quantum coherence. So this is a combination of zero quantum coherence uh, and double quantum coherence. Okay, to IKX, IL1, ILY. Then similarly, this is also 2 ILY, 2 ILY, IKZ, 2ILY, IKZ. This is also combination of zero quantum coherence and double quantum coherence. Now, when these terms are added, combination of these terms results in pure quantum coherences. Okay, pure zero quantum coherences or pure double quantum coherences. Like here in this case, in the option D that you see 2 IKX ILY minus 2 KIYIL. So the two terms, combination of these two terms results in pure zero quantum coherence or double quantum coherences. But the only observables or the terms which are corresponding to the single quantum coherences are these terms IKX, IKY. IKZ is also, this is also not observable because our detector is not along the Z axis, so we do not detect this. So it has to be IKX, IKY. These are detectable. Okay, now how do we define these terms, right? So IKX, ILY, right? IKX, ILY. What does this mean? This means that X magnetization, this is X magnetization of K spin, K spin, X magnetization of K spin, and Y magnetization of L spin. But then you will also Y Ly means Y magnetization of L spin. But if there are terms like this one, I K or I L X L X I K Z. So that means X magnetization of L spin, X magnetization of L spin, antiphase with respect to, which is antiphase with respect to K. So whenever you have this KZ, then it would mean antiphase with respect to K. Then similarly, if you have another term, say ILYIKZ, then how will you define this term? So this is similarly, you can define this term. It means Y magnetization of L spin antiphase with respect to K. Okay. So antiphase signals means what? You will have, so for antiphase signal, you will obtain this type of a, so this is an antiphase signal. So this is an antiphase signal. Okay. So this means that this 2 IKX, ILZ, this will be, this term will be allowed to evolve. And then when you collect this FID and do the Fourier transform of this, then you will get an antiphase signal. Okay. So that is how you define these terms. Okay. And what will these terms will they give you? So if you have this IKX term, if you have this IKX term and following this, there will be the FID of this term. You will correct the FID and then you will Fourier transform this. So Fourier transform this will give you a doublet. I'll give you a doublet of this will give you a doublet of K in phase. This is also called the in phase signal. This is called the in phase signal. So we'll get a proper doublet in phase signal. Okay. So basically you are measuring these different transverse magnetization. Just erase this one. Okay, yeah. So the correct answer for this question is option A. Is option A. So all these different terms, IKX, ILY, ILY, IKZ. So these are all different combinations of indicate the double quantum and zero quantum coherences, or double quantum and so remember that these I've already written this. Have I written this? I will write this properly. So all these terms 2IKX, ILY, or it can be 2ILY, IKZ, or it can be what? Or it can be 2IKX, ILX. Okay. So all these terms are these are all what? So these terms are combinations of double quantum coherences and single quantum coherences and combinations of these. So when you add these different terms or subtract these terms, then you will get pure double quantum coherences, single quantum coherences term. Okay. So I will move to the next part. Yeah. So this is another question. I will correct this. It is actually this form 2IKX ILY. 2IKX IKLY. So what does this represent? This term represent just now we were discussing. So it may, represents mixture of double and zero quantum coherences. So any of these terms 2IKXLY, or it can be 2IKYILX, or it can be 2IKXILX. Okay. So all these terms they represent mixture of double and double and zero quantum coherences. Okay. Okay. Now what we will look into. So till now what we were discussing, till now we were discussing about the general 2D correlation spectroscopy experiment. What is the spectra? How does the spectra for 2D COSY looks like? And then what are the general parts in a two-dimensional NMR experiment? So how does the segmentation of time axis is done? So now what we will deal is what are the fine structures that we observe in the cross peak of a 2D COSY. Okay, so just now I was discussing that in a 2D COSY spectra, you have two different peaks. You have two different peaks. One are the diagonal peaks. So you have these diagonal peaks. So here you have this F1 dimension. This is the F2 two axis, F1 axis, F2 axis. And you have for a two spin system, you have two different spins, say K and then L. So these are the diagonal peaks, and then there are the off diagonal peaks. Okay. So if you so if you see if you look into these peaks in more detail. So are there any fine structures present in the peaks that are present in the diagonal and in the off diagonal? So just now we were discussing that what are the fine structures that are present diagonal in the diagonal element, and we just now said that the fine structures that are present, they have all dispersive in phase line shapes, in phase dispersive line shape. But what are the fine structures that are present in the crossed peaks of the 2D COSY? So the cross peak of a 2D COSY, they have absorptive line shape, right? They have absorptive line shape, and these give us the information whether the two spins are coupled or J coupled or not. So yeah, so what has been, so let's understand this. Cross peaks arises when the two spins are J coupled. Okay, so for example, there are two spins A and B. So if they are coupled, and if you now plot a 2D spectra for this AB coupled system, you have this A spin, B spin, then again you will have A spin, B spin. So this is the F1 axis, this is the F2 axis. So there will be a diagonal. So diagonal peaks, what do they represent? They represent autocorrelation, means each F1, each spin in this F1 axis is related to the F2 spin is related to the is related to the frequency in the F2 axis, right? But but now we are seeing that in this AB coupled system, this A spin is coupled to the B spin. So other than this peak, since this A spin is coupled to the B spin, we will obtain another peak. Okay, we will obtain another peak. And similarly, the B spin is also coupled to the A spin, so we will get another peak. So these are called the cross peaks. So if I shade these, so if I shade these, so these shaded are the, I don't know what is happening to this. So these shaded regions, these are the diagonal peaks. They represent autocorrelation. And we will observe only these cross peaks if the two spins are coupled. These are called the cross peaks. Now, how we will understand that what are the fine peaks that are present in the cross peaks. So, if the peak appears as a singlet, if the peak appears as a singlet, it indicates that the spin are not coupled with anybody. So, for example, if you have a three spin system, so consider that there are three spin A, B, and C. So if you get any spectra which if you get any peak which does not have a corresponding cross peak, then that would mean that it is not coupled to any other spin. So yeah, the second term in the density operator at the fourth time period gives us this equation, right? 2 ikz ILY sine pi jkl T1 sine omega k T1. Now, evolution of this rho 4 in the T2 period and the chemical shift will give us this. Then this I had derived. I'm not explaining it in much detail. So what you have to understand here, that in that for when we were understanding the diagonal peaks in a 2D COSY, we had calculated the trace, or what will be the observable part. Now, similarly, if we want to understand that what are the fine structures in the cross peak in 2D COSY, we will again take the trace of this rho 5C. So rho 5C is basically after this. So, so this is 90 degree X. Then there was a 2T1 time period, and then this was the T2 time period. So following this was the fifth one, two. So this was the fifth point. This was the fifth point. So if we take the trace of this rho 5C dash ILY, then we get this expression sine omega L T2 sine pi JKL T2 sine omega K T1 sine pi JKL T1. Now if we solve this to find that what are the T1, what are the points having this T1 component, and in the F2 dimension or in the T2 dimension where we will get the spectra, we apply our trigonometric equation and solve this, then we will get this equation. Then we will get this expression cos omega k plus pi j k l T1 cos omega L plus pi j k l T2. then minus cos omega k plus pi j k l T1 cos omega L minus pi j k L T2, then minus cos omega k minus pi j k L T1 cos omega L minus pi j k L T2, and then this. So if you look at these expressions, then all these are cosine terms. All these are cosine terms, and each of these four terms. So this is one term, second term, third term, fourth term. So each of these points. Each of these points will give us a fine structure in the cross peak of the 2D cozy. And all these are cosine terms. So cosine terms will always give us absorptive line shape. Okay. Cosine term give us absorptive line shape. And what will be the signs of these peaks? So it will be plus, minus, minus, plus. Right. And dispersive line shape when on solving this trace or when we calculate the trace of this rho 5C, if we get a sign, if we get sign components, then it will give us dispersive line shape that we were getting in the fine structures of the diagonal peaks in 2D cozy. So remember that cost terms give us absorptive line shape and sine terms gives us dispersive line shape. Okay. So now if we yeah, so all of these are cosine terms, and so all these different terms. So this four terms, all these four terms will give us four absorptive peaks in the fine spectra of 2D cozy. Fine spectra in the of the cross peaks of the 2D cozy. Okay. So all these are absorptive and positive, negative, negative, positive based on these terms, plus, minus, minus, plus. So it is positive, negative, negative, positive. So in the F1 dimension or in the F1 axis, we will have this point, and in the so this so the first peak that we get in the F1 axis, this at this point, and in the F2 axis, this will correspond to this point. And then the second peak that we will get, that will correspond to this point in the F1 axis, this point on the F2 axis. And this third peak that we get, this will correspond to this point on the F1 axis and this point on the F2 axis. And similarly, in the here, nu k minus jkl by 2, this will correspond to the F1 axis, and this point corresponding to the F2 axis will be at this point, nu L minus jkl by 2. Okay, so yeah, so this is how a 2D cozy looks like, cozy spectra looks like. So if you, so these are the contour map, right? These are the contour map. So you see, these are the diagonal elements, right? These are the diagonal terms, this one, this entire. These are the diagonal terms. So how does the peak in the diagonal terms look like? They have this dispersive line shape. They have this dispersive line shape. So this is basically a contour map. So in the contour map, you got cross section of the peak that you get at different layers, and this is how it looks like. And these are the cross peaks. So these are the cross peaks. So in the cross peak, you see these are very fine absorptive line shapes. So absorptive line shape, the signs are indicated plus, minus, minus, plus, while these diagonal elements, they have plus, 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 plus. Right. So this one and this one. Okay, nu k, nu L. So okay, for a KL coupled spin system, the diagonal, if we take a 2D spectra of this KL coupled spin system, we will see that the diagonal elements will have dispersive line shape, dispersive in phase line shape, and the cross peaks have absorptive line shapes, right? Absorptive line shape. So here there is another example. This I have directly taken from the lecture slides. So you see here. So since this if it is a two spin system KL, then the K this in the 1D spectra will give us what? Since the K is coupled to L, it will lead to splitting of the K spin into a doublet, and similarly the K spin will cause splitting of the L spin into a doublet, and in this axis also similarly this will cause splitting in the, if we observe the 1D spectra. But in the 2D spectra, you see here that these are the off-diagonal elements of the cross-peak elements, and these are the diagonal elements. So for this molecule, you see here this molecule, the 2D COSY spectra has been recorded, and you see here. So this is what I was saying, that this is the. So what is this? So this spectra that you see on this right side, this is basically they have taken a cross section, or a side view of how this spectra will look like. So here, this is the absorptive line shape. This is how an absorptive line shape looks like in a NMR spectra, and this is the dispersive line shape. So this is for this peak. So for these two peaks you see, so this is the contour map. If we see the side view of this, then we get this shape. This is called the dispersive line shape. What is happening to my marker? This my writing pen today. This is the dispersive line shape. Okay. Similarly, for this, you see, this is for this part. So you have 4 peaks, right? 1, 2, 3, 4. So this is the third peak. So if you go through the third peak, then you again have this one. So this third peak, this is the positive, negative, positive sign, negative sign, and then there is this dispersive line shape. Then similarly for this one, again, so this is a diagonal element. So diagonal element, it gives us a dispersive line shape. Then off diagonal element, this again has again given us a absorptive line shape. And similarly for this segment, you again see this. There is a dispersive line shape and then a absorptive line shape. Okay, so this is what I was explaining. Now, based on this, you try to solve these questions. So cross peak for a two spin system in a 2D COSY spectrum will have the fine spectra. So this has been hidden, which has got hidden. Cross peak for a two spin system in a 2D will have the. So how will the what will be the what will be the sign of this cross peak for a two spin system? You have to say. So it is plus minus minus plus 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 minus 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 plus minus minus minus. So out of the 4 options, which one will be correct? So here, read the question carefully. What has been asked? Whether cross peak you have been asked to determine the cross peak for a two spin system, or whether it is the diagonal peak. So if it is a diagonal peak, then how will it look like? For a diagonal peak, they are in phase dispersive line shape. They have in phase dispersive line shape, means all these 4 fine structures, or all the 4 fine peaks that you observed in the diagonal peak will have positive signs, positive plus 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 plus. Okay, so this kind of dispersive means this kind of, this one that I was explaining. Yeah, this shape. This is the dispersive line shape. Okay. And but here you have been asked to determine the cross peak. So the fine structures that are present in the cross peak for a two spin 2D COSY spectrum. So that has what? It has absorptive. Just now I was discussing that it has absorptive line shape, right? So absorptive line shape, and they are all cosine terms, right? They are all cosine terms. So they have absorptive line shape, and the sign is plus minus minus plus. Okay. So option number A is correct. Okay, so yeah, that is what I was explaining. Since all the terms in the observable are cosine functions, we get absorptive peaks. Absorptive peaks, and how will you determine the sign? So the 4 terms that we get, each of these 4 terms gives us 4 individual peaks in the fine spectra. So these are plus minus minus plus. Okay, so that is what is shown, plus minus minus plus. Just give me a second. See if I hope these points are clear. Now, yeah, A similar question that was asked in your assignment is, in a cross peak of a 2D COSY spectrum, the line shapes along the F1 and F2 dimensions will be. So ABS stands for absorptive line shape and DIS stands for the dispersive line shape. Okay, so try to answer this question. So just now I discussed this. Yeah, so just now I was discussing that this F1 and F2 dimension in both the F1 and F2 dimensions. So when we solve the trace of the row 5C ILY term, then what do we get? We get four terms. So all these four terms are cosine terms. All these four terms are cosine terms. So cosine terms indicate that they will have dispersive, they will have absorptive line shape. They will have absorptive line shape, and the sine terms indicate that they will have what? They will have dispersive line shape. So the correct answer is option number D. Okay. Yeah. So option number D is correct. So all the terms they are cosine terms. So all have absorptive. All will have this absorptive line shape. Similarly, if you were asked to find the so what will be the spectra for the diagonal peak, then what would be the answer in that case? In that case, the answer will be what? This, right? All are dispersive line shape. So this will be for the diagonal. So all the diagonal peaks, they are sine terms. So they will have this. If you want to write this in this form, then they will be all dispersive. All the four elements will be, or all the four fine peaks that you see, they are all dispersive. They have all dispersive line shape. Okay, now let's understand this concept. 2D cozy spectrum for a 3-spin AMX system. So till now we were discussing about the 2-spin AB system. Now if you have a 3-spin system, so a 3-spin system, so you can consider that there are three spins: A spin, M spin, and X spin. Now these three spins, so they can be arranged in two different ways. One is that they can be arranged in a linear fashion, that A is coupled to M and M is coupled to X. Or the other possibility is what? They can be, each of these can be coupled the to the other two. Okay, so you can have this system also. So this is called a triangular 3-spin AMX system. So in this system, what you see here that this A spin is coupled to both M spin and X spin. Similarly, M spin is coupled to A spin and X spin. So what it is showing is in this system, each of these spins are coupled to two other spins. Okay, so that is called a triangular AMX system. So now, when if they are linearly arranged, so if they are linearly arranged, then what will this 1D spectra look like? So in the 1D spectra, let me explain you first this linearly, where if this AMX system is linearly arranged. So if this AMX system is linearly arranged, then in the 1D spectra, what will you get? So each spin is coupled to the other spin, right? So the M spin will cause the splitting of this A spin into a doublet. We will get a doublet for the A spin. Similarly, so depending on the chemical shift, what type of nuclei you have. So here you can see. Then similarly, this M spin is coupled to both this A spin and X spin. So this A spin will cause the splitting of the M spin into a doublet, and X will also cause splitting. So what you will get for the M spin? So for the M spin, you will get a doublet of a doublet, right? So we'll get this kind of peak. So this is called a doublet of a doublet. And then for the X spin, so see this is X spin. So based on this figure, so it will depend on what type of nuclei you have or what other atoms are there. So that will determine the chemical shape. But say this X is more de-shielded, so it has a higher chemical shift value. So, so let's stick to this figure that was there in your slide. So these figures I've taken from the slides directly. So this is for the X spin, this is for the M spin, and then for the A spin, so if this is the X spin is only coupled to the M spin. So that is why this M will cause splitting of this of its peak into a doublet. And similarly for the A is only coupled to M. So the M spin will cause splitting of this A spin into a doublet. So you will get a doublet. So this is the type of spectra that you will get if you record a 1D spectra of this AMX linearly arranged three spin system. And if you now take the 2D cozy of the spectra of this AMX linearly arranged system, then what you will get? So, so you have three spins. So, so in the F1 axis, you have three spins. The frequency corresponding to A, M, and X. Now, you have two axes, right? In a 2D cozy spectra, you have two axes. One is the F1 axis, another is the F2 axis. In the F1 axis, the corresponding frequencies have been written. So it is this frequency corresponding to A spin, M spin, and X spin. Then in the F2, similarly, A spin, M spin, and X spin. Now what you will get? So first, this A spin is coupled to the M spin. Okay. So there will be, so in the diagonal peak that you see in the diagonal peak, so each of these spins are coupled to itself, right? So each of these, though there is an autocorrelation between A and A. So you get a peak over in first in this region. So A is for A, there is corresponding A in the F2 axis. So you get a peak here. Now A is also coupled to M. Okay. So you get what you get over here, that A is coupled to M. So you get a peak over here. Okay. Then similarly, if you look for now, if you move to the M nuclear spin, the M nuclear spin has, so first you will always get a diagonal peak. And now if you look for the cross peak, so this M is coupled to A and it is also coupled to X. So that is why you get a peak over here, this peak. So this peak indicates that M is coupled to A and also M is coupled to X, right? There is some mistake here. So you get a peak over here, which indicates that M is coupled to A and M is also coupled to X. Now, if you move to the X pin, the X is only coupled to M. So you get a peak over here. So there is a diagonal peak for X, and also this X is coupled to only M. So you get a peak over here. Okay. So I think there is a, I think there is some mistake in this figure. These peaks will not be there. These peaks will not be there because A is only coupled to M, right? It is not coupled to X, so you will not get these peaks. You would get these peak for this triangular system, but in this case, this is since they're linearly arranged, so A is only coupled to M, so you get a peak over here, the cross peak over here, and similarly you get a cross peak over here. So this one, and M is coupled to A, so that is why this one. And then for this M also, M is coupled to both A and X. So that is why for this one, this M is coupled to A, you get a peak over here, cross peak here, and you get a cross peak over here. Okay. If you now want to look at the what are the fine structures in the cross peak in the linear AMX system, you have to understand two terms. One is the active coupling and another is the passive coupling. So what is active coupling? So for example, if you want to look at this cross peak, okay, if you are looking at this cross peak, what is this cross peak? This is a MX cross peak, right? This is a MX cross peak. So M on the F1 axis, X on the F2 axis. So this is a MX cross peak. Similarly, this is what? This peak is, this is a on the F1 axis, M on the F2 axis. So this is the AM cross peak. This is what? So this is actually the right one. I have somehow by mistake I have shown the spectra for this triangular AMX system. I will rectify it, but this is the spectra that you will get for a linearly arranged AMX system. Okay, so this is an AM cross P, and if you look at this, this is also what? This is also an AM cross P. And what is this? This is this is there is M on the F2 axis and A on the F1 axis. So this is again a no. There is M on the F1 axis, and there is X on the F1 axis, and this is a MX cross P. So yeah, so this is an MX cross P, and this is so this is what a AMX the linearly arranged three spin system looks like. So for example, you want to find that what is the fine peaks or what are the fine structures present in this MX cross peak. So if when you are considering this MX cross peak, then this is the active coupling. So the cross peak that you are considering, that is the active coupling. All other fine peaks that you will get those are the passive coupling. So now if you are considering, if you want to find out that what are the fine structures present in an AM cross peak, then AM would be the active coupling. AM would be the would be the active coupling uh, the splitting that you will get, that will be because of this this AM active coupling. All other fine peaks that you will get, that those will be because of passive coupling. So the cross peak that you are considering, that is the active coupling. So that is what it is written here. The one whose cross peak is being considered, that is the active coupling. Active coupling causes plus minus splitting, or also called anti-phase splitting. Now passive coupling, the all other coupled spin. Okay, all other coupled spin will that will lead to the fine structures. They are the passive coupling, and passive coupling results in plus plus, minus minus, or in phase splitting. Now here how do you calculate the fine structures of cross peak? So that I will show. I will just add one more slide, and I will show you how to calculate these. Okay, so now you have AMX pin system, linearly arranged AMX pin system. And for example, you want to, for example, you are taking this. So this is the F1 axis, this is the F2 axis. You have this A, M, X on this F1 axis. So you have A, M, X on the F2 axis. And so you will have a diagonal peak. So all peaks are related to with itself. So you will have a diagonal peak. Now, for example, AMX, so A is coupled to M. So that is why what you will get over here is coupled to M. You will have a cross peak over here. You will have a cross peak over here. Similarly, M is coupled to X. So you will have a cross peak over here. Here. Okay. Then A is also coupled to X. No, A is not coupled to X. M is coupled to X. So you have a cross peak over here. So similarly, here you will have mirror image. So M is coupled to X. Then A is coupled to M, and A is also coupled to M. So now, for example, you are considering this AM cross peak. Okay, so this is the AM cross peak. So if you consider the AM cross peak, so first, now for AM cross peak, first you will see that how will this the splitting of the of this spectra of the A spin take place. So the A spin will be split into two, because it is coupled to M. Because it is coupled to M, and we are considering the AM cross P. So the M spin will cause the splitting of A spin into plus and minus. So this is JAM. So that is the coupling constant between the A spin and the M spin. Now we will look into M spin. So how will the or how will the peak of M spin split? So first, when we are considering the M spin, so due to, as it is coupled to A spin, it will first split into plus minus. So that is what I was saying, that when we are considering, so this will be JAM. Why this will be AJM? JAM because we are considering the AM spectra, right? We are considering the AM cross peak. AM cross peak. So for AM cross peak, this AM is the active coupling, and active coupling will always lead to what? Plus minus splitting. Plus minus splitting. Now this plus peak will again be split into two because this M spin is also coupled to X. So X will again cause the splitting of this M peak into two. So this will be passive coupling. So passive coupling will result in what pattern? It will result in plus plus minus minus. So this is so now if you want to determine how what will be the fine structure that you will observe in the AM cross peak, then what you will do? So you have to so you will for example, so we were considering this one, right? So in this case, we were considering this cross peak. So in this cross peak, the M is on the F2 axis. M is on the F2 axis and A is on the F1 axis. Okay. So for A, you write here plus minus, and for M, what you get over here? Plus plus minus minus. Plus plus minus minus. Okay. Give me a second. So this will be plus plus minus minus for M. So this is F2. So now you multiply these. Multiply these. So how many terms you will get? Plus plus plus. Plus and plus will give you plus. Minus and plus gives you minus. Minus plus gives you minus. Minus plus will give you minus. This plus multiplied by minus will give you minus. Minus minus will give you plus. Minus minus will give you plus. So these are the eight fine peaks that you will get in the these are the eight fine structures that you will get in the cross peak of a in the aim cross peak. But now if you, for example, you are considering this cross peak and you want to look at what are the fine structures that is present in this AM cross peak, then what you have to do? So for this peak, M is on the F1 axis and A is on the F2 axis. So here what you have to do for M, you have to write this. You have to write the this splitting on this Y axis. So for M it is plus plus minus minus. And here you have A, you have plus minus. Now you have to multiply these. Plus plus will give you plus, plus minus will give you minus, plus plus will give you plus, plus minus minus, minus plus minus, minus minus plus, minus plus minus, and minus minus plus. So these are the eight components or eight fine structures that you will get in the cross peaks of this AM peak. Okay, we will get eight components. So that is, so now that you have understood this, you can follow this figure. So there can be two cases basically. First, if the coupling between this A and M spin is greater than the MX spin. How much time is remaining? Okay, I will complete this quickly. If this coupling is greater, so the AM coupling is greater than the MX coupling, then what you will get? So first this A, consider this A spin. So the A spin will be split into two, plus and minus, right? Because this A is only coupled to M. So this M spin will cause the splitting of A spin into two doublets, into a doublet, which will be plus and minus because of active coupling. Then this M spin will first be split into a doublet by the A spin, right? And followed by the A spin, and you will get a plus and minus because active coupling, because you are considering the AM cross peak, and then this will again be split by the X spin into plus plus and minus minus. Passive coupling, all other peaks that were all other fine structures that you will get other than AM, they are all passive coupling. Okay, but if JAM is less than JMX, okay, if the coupling constant between this A and M coupling is less, means you can consider this M X, and for this A M X. So what does this mean? JM means the coupling between A and M spin is greater than that between M and X. The M and X is weakly coupled. And in this case, the A and M is weakly coupled, but MX is strongly coupled. So in this case, again, we are considering the AM cross peak. So the A spin will cause the splitting of this M frequency into plus and minus. And then because this MX is less than the MX coupling is less than the AM coupling, so that is the reason why this AM is causing this. There is a invert overlap of this splitting of this peak by JMX into it moves into this part, right? So there is again this plus plus minus minus. So the pattern that you get over here is plus minus, right? Plus minus, and in this case you get plus plus minus minus. So I hope this is clear. So this is also explained in the lecture. You can go through the lecture also if you are finding it difficult to understand. So I hope it is clear. So the coupling of MX is less than the coupling of AM. That is why you get this plus. This part moves into the peak of this MX coupling. So yeah, so case one and case two is what I was explaining you over here. Okay, so for AM, you have two peaks, right? So depending on whether this A is on the F1 axis or whether this FA is on the F2 axis. So in this case, A is on the F2 axis, right? This is the F2 axis. And here in this case, A is on the F1 axis. So different cross peaks will have different fine structures. That is what it is shown over here. Okay, so case one is what? Case one is JM is greater than JAM is greater than JMX. And case two is what? It is JAM is less than JMX. That is what it was. Okay. So you will get different. So here you get this pattern, here you get this pattern. So that is what it is shown. The fine structures are different for the same aim cross peak. Okay. So if depending on whether it is on the F1 axis or whether it is on the F2 axis. So now try to answer this question in a 2D cozy spectrum for a linear AMX spin system with JAM greater than JMX. The M spin multiplicity will have the structure. So n spin multiplicity structure, you have to find out, right? M spin multiplicity. So for the M, just now I was explaining you. So here Jm is greater than Jmx. So M will first be, because M is coupled to A. So there will be splitting of the M spin into plus and minus, right? Plus and minus. Then M is also, so this is Jam. So the A spin causes the splitting of the M spin into a doublet, and this is active coupling, and that is why we get plus minus pattern. And then this M is also coupled to X spin, so there will be again splitting of this plus to plus plus passive coupling. So all other spin to which it is coupled are considered passive. The only cross peak that we are considering is the active. So if you are considering AM cross peak, then we consider this AM is there is active coupling between A and M, and all other peaks, all other spins to which it is coupled, they are all passive. So there will be, so since JAM is greater than JMX, so this will be this pattern, right? There will be no overlapping of this peak into this peak, right? So this is JMX. So what pattern do you get for the M spin multiplicity? You get a plus plus minus minus. So the correct answer for this option is option number B. So is it understood? So what would have been the answer if this would be JAM less than JMX? Then in this case, what you would get? In this case, this M would first be split into plus minus because actively coupled to A. Then there would be again be splitting by X into 2. But since this MX coupling is higher, it is greater than the AM coupling. MX coupling is greater, so this splitting will move into this part. And this one. So it is again plus, plus, minus, minus. So the pattern would be plus, minus, plus, minus. So this would be the pattern if JAM is less than JMX, and this will be the pattern. This will be the pattern if AM is greater than JMX. So in the question, the You have been asked to find out the pattern M spin multiplicity pattern if JAM is greater than JMX. So the correct answer is option B. If this would be the question, then the correct answer would be option A, plus minus plus minus. Okay. So yeah, the M spin is coupled to A spin. So because of the active coupling, the M spin is first split into plus minus pattern. Passive coupling of MX result in the splitting pattern plus plus minus minus. This is what I've shown here. Okay. I hope this is clear. This question is clear. So you try to understand these concepts very nicely. They are very important concepts, and they are not very difficult. Once you understand these they you can easily solve such questions. Now, this was question number 8. Moving to question number 9, in a linear three-spin system AMX in the cross peak between A and M spin. So if there is a linear three-spin AMX, in a linear three-spin system AMX means the AMX is, there is a linear AMX spin system, the cross peak between A and M spin. So you are considering the cross peak between A and M spin. So if you are considering the cross peak between A and M spin, then what would it mean? Then JAM is passive coupling, JMX is active coupling, JAM is active coupling, JMX is passive coupling. So you are considering the cross peak between E and M spin. So if you are considering the cross peak between E and M spin, then JAM is active coupling, right? JAM is active coupling. So that is why option number C is correct. If you are considering the cross peak between M and X spin, then JMX is the active coupling. Okay. JMX would be the active coupling for cross peak between M and X spins. Okay. And then JAX would be the active coupling. Whichever cross peak you are considering, that is the active coupling. Okay. All other are the passive coupling. In the linear AMX system, in the AM cross peak, JM is the active coupling. Now consider now try to understand this triangular AMX system. Okay, so what will you have for this triangular AMX system? So now, before explaining it, I will first draw this. So this is what I was showing you. You see here. So by mistake, I have added this. This is actually the 2D posing of triangular AMX spin system. AMX system. I have by mistake I've added this spectra in the linear AMX system. I will correct this one. So now consider this AMX, triangular AMX system. Okay. In the triangular AMX system, what do you have? So in the triangular AMX system, each spin is coupled to two other spins. A is coupled to M and X, M is coupled to A and X is coupled to A and M. Okay. So if you take the 1D spectra for A, M, and X spin, then what will happen? A is coupled to M, so M will cause the splitting of A into a doublet, and X will again cause the splitting of this doublet into another doublet. So you will get a doublet of a doublet. Okay, you will get a doublet of a doublet. So this will be for X. Consider this X. Then similarly, M is coupled to A, M is also coupled to X. So again, you will get a doublet of a doublet for this M. The chemical shift that is plotted on the axis. And similarly for X also, X is coupled to A and M. So you will again get a doublet of a doublet because A will cause the splitting of X into a doublet, and then M will cause the splitting of this doublet into another doublet. So you get a doublet of a doublet for A spin. Now if you plot the 2D cozy spectra for this AMX triangular spin system, then what you will get? So this is your F2 axis, this is your F1 axis. Okay. So this is your F2 axis. This is your F1 axis. So here on F1 axis, you plot this is A, frequency corresponding to the A spin, frequency corresponding to M, and this is frequency of X. Similarly, on the F1 axis, you have this A, M, and X. Now, first, you will get a diagonal peak. So A is every spin on one axis is correlated to the other to the same spin on the other axis. M is correlated to M on the F2 axis. X spin on F1 axis is correlated to X spin on the F2 axis. So we'll get three diagonal peaks. So what is happening to my marker today? But now look at now what are the cross peaks that you will get. So other than being coupled to itself, A is also coupled to X, A is also coupled to M, and A is also coupled to X. So you will get a cross peak over here, right? This is the AM cross peak, AM cross peak. Then A is also coupled to X. Okay, so you get a cross peak over here. Similarly, since A is coupled to X, cross peak over here. A is coupled to M, X. Similarly for M is coupled to M is also coupled to X. So you get a peak over here, M, and M is also coupled to A. So you get a peak over here. X is coupled to A, so you get a peak over here, and X is also coupled to M, right? So you get a peak over here. So these are the cross peaks that you will get. These are the diagonal peaks. These are the cross peaks. Okay. Is it clear? So X is coupled to A, so you get a cross peak here. X is also coupled to M, so you get a cross peak over here. A is coupled to M, you get a cross peak over here. A is also coupled to X, you get a cross peak over here. And M is coupled to X and M is coupled to A, so you get two cross peaks for this MX coupling and AM coupling. Now you want to find that what will be the cross peaks, what will the fine structures in these cross peaks. What will be the fine structures that you will observe in these cross peaks. So how will you find that? So you have to do this similarly that I was showing for this linearly arranged AMX system. For this also you have to apply the same principle. So for example, you are considering say for this AM spin, then for AM cross peak, for this AM cross peak if you consider, then first new A. So A will be first be split into a doublet, right? For AM. So this will be plus minus the AM. Then this will be again split because A is also coupled to X. So it will be again split into plus plus minus minus. This is minus, sorry. This is minus. This is the MX. This is again MX. Okay. Now for M. Now for M, what will you get? M also you will have this same. M will first be split into because you are considering the AM cross peak for that reason A is actively coupled to M. So active coupling result in plus plus pattern. Then so this is JAM. Then again this peak will further be split into a doublet. So M is coupled to X. So that will result in a plus plus minus minus. So this is JMX. A doublet of a doublet. Now, for this peak, you are considering this peak. So you plot A on the F2 axis and M on the F1 axis. Sorry, this peak for this peak, A is on the F1 axis, right? A is on the F1 axis and M is on the F2 axis. So how many components you will have? How many? So for M you have plus plus minus minus, plus plus minus minus, and for A you have what? A you have again you have plus plus minus minus. So you multiply these, you will have 16 components, right? Plus 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 minus minus minus, then again plus 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 minus minus. Then minus plus will give you minus minus plus plus minus plus minus minus plus plus. So you have 16 different fine structures in the AIM cross peaks. 4 into 4. So you have 16 different cross peaks. Similarly, you can consider any other peak, cross peak, and you can calculate the fine structures, what will be their line shape, what will be the sign, yeah, for using this method. Okay, so yeah, on one axis you put the sign and then you multiply it simply. That will give you the answer. So that is what I was showing here. So this is the AMX system. So you see, all of these have so X. So this X spin is split into a doublet of a doublet. M spin is also split into a doublet of a doublet. And now the splitting will also depend on the coupling constant. So here you see that the AX coupling constant is greater. So you have this splitting. So depending on the coupling constant, you see the separation between the peaks. Okay, so all of these are split into a doublet of a doublet because each of the spin is coupled to two other spins. Okay, so all the three spins will appear as doublet of a doublet, and this is what the 2D cozy will look like of a triangular AMX system. The fine spectra, how will you calculate the fine spectra? So this is what I was explaining. So if you have if you have this condition that J coupling constant between A and X is lesser than J coupling constant between A and M, and this is also lesser than the coupling constant between M and X, then in a similar way you can calculate this. So because this MX coupling is greater than the AM coupling, so this splitting of this M into by or the splitting of this AM peak by the X spin will result in the insertion of this spectra into the MX splitting, and thus you will have this pattern plus minus plus minus. Okay. Now, if you want to find out how many components you will get, you plot this on the F2 axis, F1 axis, and M on the F1 axis, and you simply multiply these. Okay. So for A, you have plus, plus, minus, minus. So that is why you have written here A is on the F1 axis. So you are considering this peak basically. Okay. So on the F1, you have A. On the F1, you are considering this peak. On the F1, you have A. And on the F2, you have A. So you are trying to look into what will be the fine structures in the cross peak. What will be the fine structures in this cross peak? So that is why you have for the M, you write it here as plus minus plus minus plus minus plus minus, and then you simply multiply it. Plus plus will give you plus, plus minus minus, plus plus plus, plus minus minus, then plus 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 here. So you simply multiply it plus minus minus, and in this way you can get that how many. So how many fine structures you are getting in this AM cross peak? You are getting 16 fine structures or 16 components. So yeah, that is what has been written here. So you can read this. We are considering the AIM cross peak. So JM is the active coupling here. Since JM is the active coupling, so first you will get this plus minus splitting, and for both A and M multiplied, and then JAX and JMX are passive coupling, resulting in plus plus minus minus splitting pattern. So JAX and JMX are the passive coupling, right? So you are getting the plus plus minus minus splitting pattern. So the F2 side, if you look at this F2 side, how many components does this F2 side have? It has four components, right? Four different components, plus minus plus minus. And the F1 side with the A spin, F1 side has a A spin, and how many components? It has four components. So total, how many components will you have? You will have 16 components. So 16 fine structures will be present in the cross peak of a triangular AMX system. While for a linear AMX system, how many components were you having? Were you getting? So you were getting 8 fine structures, right? 8 fine structures, because here you had only two components and here you had four components. So total 4 into 2, 8 components. While for the triangular AMX spin system, you will be getting 16 fine structures. So I hope this is clear. Now try to answer these questions in a 2D cozy spectrum. In a 2D cozy spectrum for a 3-spin AMX system, the fine structure in a cross peak. So the fine structure in a 3-spin AMX system is determined the relative magnitude of this chemical shifts is determined by the relative magnitude of the active and passive coupling constant. Okay, so for a whatever, the third option is does not depend upon the signs of the coupling constant, and it's entirely determined by the passive coupling. So what I discussed just now, that for a 3-spin system, you always have to consider the active coupling and passive coupling. 3-spin system, you have to consider active coupling and passive coupling. So what is active coupling? So the cross peak that you are considering will be the active coupling. So if you are considering AM cross peak, then AM is the active coupling and all other are the passive coupling. And active coupling results in plus minus splitting, and passive coupling results in plus plus minus minus splitting. So remember this. This is what you have to remember. So the first option is false. Is determined by the relative magnitude of the active and passive coupling constant. That is true. In a three-spin AMX system, you always have to consider the relative magnitude of the active and passive coupling constant. It does not depend upon the sign of the coupling constant. This is also false. We just now we solved this that it will depend upon. So what is the sign of this A component? What is the sign of this B component? And if we were multiplying it to find what will the sign of the spectra, and is entirely determined by the passive coupling. This is also false. So the correct answer is option B. Okay. So yeah, answer is option B. The fine structure in the cross peak of a three-spin AMX system is determined by the relative magnitude of the active and passive coupling constant. So okay, so I forgot to add animation to this. So in a triangular AMX spin, every cross peak has. So in a triangular AMX, every cross peak will have how many components? So just now I had shown. So this A will be split into two into a doublet by the M spin plus minus. Then this will be again split into two by the X spin. So we will have plus plus minus minus. This is JA. For example, you are considering the AM spin cross peak. So it is JAM. This is JMX. Okay. Or AX rather, not MX. This will be AX. Then if you consider this M will be split into plus and minus by the AM coupling, active coupling, and then plus plus, or if there is this MX is greater, then this will move into this part, plus plus minus minus, right? Minus. Minus. So for A multiplet, you have four components. For M multiplet, you have splitting, you have four components. So total you will have 16 components. Okay. So rather than asking you this, then the question, this can also be asked directly. There can be four options and these signs can be different. This can be jumbled up and four options can be made. And so you have to read the question carefully, and you have to see that what is there on the F1 axis, what is there on the F2 axis, and then you have to answer this question. So now we will move into the DQF COSY. So what is a DQF COSY? It is a double quantum filtered COSY experiment. So in a DQF COSY, the diagonal peaks have. So what happens? Why is this technique? Why was this technique developed? What is the usefulness of this technique? So the main problem with the 2D COSY was that the diagonal peaks, what we just saw now, had a dispersive line shape, and these dispersive line shapes have long tails. Because of these long tails, it leads to cancellation of the peaks, and the resolution decreases. So if there are if it is a large molecule, there can be overlaps of the peak, or there can be peaks because of overlapping. The peaks can get you cannot observe the separate peaks. There can be loss of peaks. So this is the problem that we observe in a 2D COSY, is that the diagonal peaks have all dispersive line shapes, while the cross peaks have absorptive line shape. So the structure of the diagonal peaks have plus 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 line shape, while the cross peaks have plus minus minus plus line shape. The dispersive line shape in the diagonal peaks pose a problem, as in the F1 dimension, the peaks can overlap and leads to poor resolution. Okay, so that is the reason that the dispersive line shape have long tails. They have long tails, and it can lead to destruction of the peaks. Okay. So to overcome this, the DQF COSY was this method was developed. So in this method, all the dispersive diagonal peaks have been converted into absorptive diagonal peaks to improve the resolution of the 2D COSY spectra. So how is this done? So what are the pulse sequence? What changes in the pulse sequence have been made in the COSY 2D COSY experiment, that we will understand. So if you see this, the 2 DQF COSY pulse sequence. So mostly it is same. Only the difference is that there were Here, Cozy experiment, there were two pulse sequences, right? 90x T1 period, 90x, then you were detecting the signal. But here, what you have 90° phi, 90° phi, then there is another 90° expulse, and then there is the detection period, T2 time period. But what is this phi indicates? So here there is a concept of phase cycling. Phase cycling. So what is done here over here is that, so first you understand that this is the evolution period, but this time period between this 90° phi and 90° x, this is in microseconds. This is very small. This is very small. Uh, so there is a very small time gap between this 90° phi, 90° x. So what is done over here? So there are scans. Scans 1, 2, 3, and 4 are collected with the same value T1. So after this T1 time period, with keeping the same T1 period, there are 4 different scans are made, and with each above and with the after this T1 period, the first scan will be made at 90° x. Then this will be 90° y. Then there will be 90° minus x, and then there will be 90° minus y. So this is so for these four, after this T1 period, these 4 different scans will be made, and after this, these 4 scans will, all these 4 scans FID that you will obtain, those are plus minus plus minus plus minus. So this way, the addition and subtraction of these will give you one FID. Okay, so for each T1 value, so that is what it is written here. For each T1 value, 4 FIDs are recorded by changing the 90° pulses. So you change the 90° pulses in this format. So first is X, then 90° Y, then you give a 90° minus X, and then a 90° minus Y pulse is given. And there are 4 FIDs are recorded, and these 4 FIDs, the final FID that we obtain in the receiver is obtained so the final FID obtained in the receiver is addition or subtraction of these individual FIDs. Okay, of these individual FIDs. So this strategy is known as phase cycling and helps to filter out certain signals and select the others. This is called the selection of coherence transfer pathways. Okay. So this is what is done. Now after this addition and subtraction, so what I was saying, this is the so these 4 FIDs in the receiver part, these are added and subtracted, and the final signal that we get, has this. So if we solve the density operator and or make all those calculations, we will get final this expression. Finally, this expression. So the cross peak is this part. This part is the cross peak. So this part is the cross peak, and this is the diagonal peak. This is the diagonal peak. Okay. So cos omega 1 T2 sine pi j KL T2. And then if you open this bracket, you will get this sine pi j KL T1 cos omega K T1. Okay. And now if you apply this cosec or sine B formula, and if you break this down, you will have 4 terms. First term, second term, third term, and fourth term. Okay, and similarly for the diagonal peak also, break it down into, and you will get 4 different terms. First term, second, the 4 different terms, and so the 4 different terms have been written over here separately. So this is the first term, this is the second term, this is the third term, and this is the fourth term. Okay, so all these are what? All these are sine functions. So sine function would mean that they will have dispersive line shape. Now the last 90° phase shift that you give, this 90°. So this 90° X pulse that you apply, that is for converting the dispersive line shapes into absorptive line shape. So for both these cross peak and diagonal peak, you get 4 terms, and the last pulse sequence, the 90° X pulse sequence, that converts the sorry. So this is 1, this is 2, this is 3, and this is 4. This is 4. So the last pulse sequence converts this dispersive line shape into the absorptive line shape. So in a DQF cozy, what you get in a DQF cozy, the So remember this. So DQF cozy, what you are doing, you are converting the dispersive line shapes. You are converting the dispersive line shape of the diagonal peak into absorptive line shapes. That gives us better resolution. So here you see, compared to a cozy spectrum, a DQF cozy spectrum will have these are the absorptive, the cross peaks are absorptive, and the diagonal peaks are also absorptive. Okay, so the DQF cozy spectrum shows better resolution than the cozy spectrum. So this method helps to improve the resolution of the cozy spectrum, and it is clean in both diagonals and cross peaks. Absorptive line shape in both diagonal and cross peak with plus minus minus plus dispersion. So both this cross peak and the diagonal peak will have this plus minus minus plus signs, right? Okay. Now try to answer this question in a DQF cozy spectrum of a two-spin system. Both the diagonal and cross peak have the same fine structure and line shape. The diagonal peak has antiphase structure and dispersive line shape, while the cross peak has antiphase structure and absorptive line shape. Both the diagonal and cross peak figure. So what I discussed just now, that in a DQF cozy spectrum, both the diagonal and cross peak has the same fine structure and line shape. They both have this have absorptive line shape, and they both have the same fine structure. But remember this, that the diagonal peaks, okay, the diagonal peaks are in phase. Okay, diagonal peaks are in phase, while the cross peaks are anti-phase. Okay, they're antiphase. They have an antiphase structure. Both are dispersive, in-phase dispersive structure, in-phase absorptive structure, while the cross peaks have antiphase absorptive structure. Antiphase absorptive structure. Okay, so the option A is correct. All other options are false. The diagonal peak has antiphase structure. This is false. They have in-phase structure. Both the diagonal have cross peak have in-phase structure. Both do not have in-phase structure. Diagonal have in-phase structure. Cross peaks have antiphase structure. The diagonal has in-phase structure and dispersive shape, and the cross peak have antiphase structure and absorptive line shape. As in-phase, no, absorptive is false. So option number D is also incorrect. So this is the solution. In a DQF cozy, both the diagonals and cross peaks have fine structures and line shape due to the absorptive line shape. Why do they have fine structure, fine line shapes? Because they are all cosine. But this last 90-degree pulse that you were applying, that converted the dispersive line shape into the absorptive line shape, and so you get fine structure in a DQF cozy, and it helps to improve the resolution. The diagonal peaks have in-phase absorptive characters, while the cross peaks have anti-phase absorptive characters. So remember this: the diagonal peaks have in-phase absorptive characters, and while the cross peaks have anti-phase absorptive characters. And so, because these cross peaks have anti-phase absorptive characters, I think I've learned about the TOXI 2D NMR spectroscopy method. So in this TOXI method, this antiphase absorptive characters in the cross peaks have been converted to the in-phase absorptive characters by modifying the pulse sequence. Okay, so that is what it is written here. Now I'll move to the next question. Phase cycling in the DQF cozy experiment helps to improve the signal to noise ratio, helps to remove artifacts of pulse imperfections, helps in selection of coherence transfer pathway, and helps to reduce the line width in the spectrum. So the phase cycling that we were seeing, that for four different scans, the four different scans will be giving us four FIDs, and these four FIDs in the final receiver FID that we will obtain, that those are added and subtracted, plus minus, all these FID to give us the final FID in the receiver part. Okay, so these phase cycling, what was it? Why was it done? So it was done to for a selection of the coherence transfer pathway. Okay. So if you go through the derivation of this, that was which was done in the lectures. So then you will understand how it is helping in selecting the coherence transfer pathway. So the double quantum filtered. So that was so that as the name indicates, it is double quantum filtered correlation spectroscopy. So the double quantum terms that we were getting, that was the following evolution and those that was getting removed. Okay, so that is what it is written. So the initial single quantum K spin magnetization is converted to double quantum coherence between the spins K and L. And then it is, so first we get the double quantum coherence and then it is transferred. So how we are getting this, you can go to the lectures and you can see the derivation. It has been explained in great detail and then transfer. So this, yeah, this is the correct answer. And vice versa in the KL spin system, the selection of the pathway is achieved by phase cycling of the pulses and the receiver. Okay. Okay. Now I will move to the 2D nosy experiment. So two-dimensional nuclear overhauser effect spectroscopy. So you have already learned the NOE technique, right? NOE technique, and I had also discussed it in detail. But this 2D nosy experiment, this is similar. So the main difference between a nosy and a cozy experiment is that the nosy is follows the, it is a polarization transfer experiment. Is a polarization transfer experiment. While this cozy is what? It is a cozy is a coherence transfer experiment. So cozy will follow that, will help us to understand whether the two spins are coupled or not, if they are directly coupled or not. But this polarization transfer experiment, what principle does it follow? Polarization transfer experiments follows the principle of dipolar interaction. So what is the how are the two spins oriented in space? Whether they are it may be it is the two spins may not be coupled to each other, but they may be located very close to each other. So if they're located too close to each other in space, then it will lead to the transfer of polarization from a less sensitive to a more sensitive nuclei, right? So we are understood that from n spin to proton spin, how will you calculate the polarization? All these concepts we had looked into. So that is the basic difference. But when we are seeing the pulse sequence, then in this 2D nosy also this phase cycling concept comes. So this 2D nosy has been discussed again. So it is a polarization transfer experiment. 2D nosy is a polarization transfer experiment. COSY is a coherence transfer experiment. The 2D nosy also follows a three-pulse sequence pattern, just like the three-pulse sequence pattern that we were seeing in DQF COSY. And 2D nosy is based on dipolar interaction. What was dipolar interaction? That so we were seeing that how the magnetization is getting transferred from one spin to another spin through electrons, right? Through the bonds, so each nuclei is connected to the other through bonds, and these bonds are basically formed by the sharing of electrons. So how the polarization is transferred from the nuclei to the electrons, that is what is known as dipolar interaction. And this dipolar interaction leads to nuclear Overhauser effect. The nuclear Overhauser effect spectroscopy is used for determining the structure of large molecules and even small molecules. So NOSI is basically helping us to understand that what is the how are the spins oriented in space, which nuclei is nearer to each other. So for protein spectra, for when in a protein spectra, how are the amino acids arranged, which acid is nearer to the, what is the folding of the protein, all these uh, different information you will get from this 2D nosy experiment. Okay, because it is based on this dipolar interaction. So there is an additional. So here, if you observe the pulse sequence of a 2D NORSI, you see that there is another mixing time. A mixing time is introduced between this 90-degree phi pulse and 90-degree X pulse. So in this mixing period, relaxation takes place, which transfers the magnetization between the two spins. So here also you have this phase cycling. So 90-degree X, 90-degree Y, but this phi is different. And also you are adding up all these. Why you are adding up these? These individual FIDs will be added up, and the final FID that you will get in this in the final FID that you will get in the receiver will be addition of these different FIDs. So yeah, that is what I was saying. So we have rho 4 phi equal to x. These derivations have been done. I'm not going into detail of these. Rho 4 phi equal to x plus rho 4 phi equal to y, rho 4 phi equal to minus x, and these are added. And when you add this, what the final expression that you get is this one, 4 I kx cos pi j k l t1. This is z magnetization. And this one, this 2 ky ix ilx minus 2 I kx ily. This is pure zero quantum coherence. So I was explaining you that there was a question that 2I 2ILX, these are what? These are the these have both a combination of double quantum coherence and single quantum coherence, but combinations of these give us pure quantum coherence and double quantum coherence. So if the L spin is close to the K spin in space, then what will happen during the mixing period? The magnetization will transfer to the L spin through dipolar interactions. The last 90-degree pulse, both the IKX and ILZ gets converted into the transverse magnetization. So we will always, the last will always be required to convert it into the transverse magnetization because our receiver is placed in this direction. There will be both IKY and ILY. The transfer magnetization evolves in T2 with their characteristic omega K and omega L values. The 2D Fourier transform produce both diagonal and cross peaks, right? When we do the Fourier transform of these, it will give us both diagonal peak and cross peak. And the cross peak appear because of the dipolar interaction or exchange process between the two sides. So in the case of COSY, the cross peaks were appearing because of what? They were appearing because of J coupling, okay, or spin-spin coupling. But in this case, in the case of NOSY, the cross peaks are appearing because of dipolar interaction. Dipolar interaction. So remember this, they are appearing because of dipolar interaction. This is a polarization transfer experiment. The NOE can be positive or negative. So all these concepts we had discussed in week number I think 7 or 8, I had discussed whether in which case the NOE will be positive, in which case the NOE will be negative. So that depends on the correlation time. So for large molecules, the correlation time is very large. So omega tau c becomes greater than 1 and we get a negative NOE. But for small molecules, the correlation time is small. Correlation is small and it is of the order of 10 to the power minus 10 to 10 to the power minus 12. And this gives us positive NOE. Okay, so remember these concepts. So these questions, they're pretty easy, right? In a 2D nosy experiment, a cross peak arises. So why do we get a cross peak in a 2D nosy? Not because of J-coupled protons. This we will get in case of COSY, 2D COSY, but between protons coupled by dipolar interaction. So this is the correct option. Between chemically equivalent protons, no, this is wrong. Between magnetically equivalent protons, this is wrong. So in a 2D nosy experiment, cross peaks are obtained because of the dipolar interaction between the K spin and the L spin. Okay. So yeah, this is the, so if you solve the density operators and at time period 6 and using all the product operator formalism, you get these two terms, and this gives you the diagonal peaks. This gives you the cross peak. The final 90-degree expulse converts the XZ magnetization into the observable transverse magnetization. So you see here lambda IKY and ILY. So so you are getting this YY. So this which means that you are that these 90-degree expulse is helping to convert the Z magnetization or the Z component into the X or Y component. So X and Y means these are the transverse magnetization, and only the transverse magnetization can be detected. Have the same fine structure with in-phase components and absorptive peak shift. Okay. Now, in a nosy experiment, cross peaks are seen between protons which are less than 5 angstrom apart, which are more than 5 angstrom apart, which are between 5 angstrom to 10 angstrom apart. Distance does not matter. So what I was saying just now, that this nosy experiment is a distance dependent phenomena. We had learned this, right? It depends on the distance between the two spins. What is the distance between the two spins? How are the two spins oriented in space? Because the transfer is taking place by dipolar interaction. Dipolar interaction. So the transfer will only take place if the distance between two spins are less than 5 angstrom. So the intensity of the peak depends on the distance between the two spins. Okay, so we will look into this. The nuclear overhouses. So yeah, option is less than 5 angstrom apart. Remember this, that only if the distance between two spin is is less than 5 angstrom, then only the transfer of polarization can take place between two spins. NO is only observed when the distance between the two atoms in space is less than 5 angstrom. At 2.5 angstrom, the transfer process will be more due to higher interaction. So the lesser the distance, the more will be the interaction and more will be the transfer process. You will get a better intensity. The peak will have a higher intensity. The lower is the distance, but you also have to take into consideration that the distance between them must not be such that it is causing steric clashes between the two atoms. Okay. So less than 2.3 will lead to steric clashes because proton carbon distance is less than 0.3. So we have to consider that part. And the intensity of a cross peak between two protons separated by a distance r in a 2D noisy spectrum is proportional to. So that is for seeing for the NOE. And we also had looked into that the distance for the transfer of the intensity or for the transfer of polarization, the distance inversely varies as the sixth power of the distance between the two spins. Okay, so the answer is 1 by r to the power 6. That is the answer. So yeah, the cross peak intensity. Cross peak intensity is proportional to the cross relaxation rate sigma AB at short mixing times. So the cross peak is intensity. This is the cross peak intensity. So you are getting cross peaks and diagonal peak, but what will be the intensity of the cross peak? What are the factors which control the intensity of the cross peak? So cross peak intensity will depend on two factors. One is the cross relaxation rate. Okay, it will depend on the cross relaxation rate and it will depend on the mixing time. It will depend on the mixing time. So how does it vary? So this is the expression that the intensity of the cross peak is proportional to the cross relaxation rate and the mixing time. Okay, and sigma AB is what? This is the cross relaxation rate. This cross relaxation rate is inversely proportional to the sixth power of the distance between the two spins. So R is the interproton distance. If the experiment is performed at different values of Tm, so how do you get this sigma AB value? So first you need to know the value of the cross relaxation rate. So how this cross relaxation rate value is obtained? So what you do is you are taking different mixing times. Different mixing times, you calculate the so at different mixing times. At different mixing times, the cross relaxation rate sigma AB value can be determined. And then the basically this cross peak intensities. The cross peak intensities measured at different Tm values are fitted into a linear equation to obtain sigma AB. So what you are doing that you are at different mixing time you are calculating the value of the intensity, the cross peak intensity, and then you fit these values into a linear equation and you get the value of sigma AB. So once you know the value of the cross relaxation rate, then from here you can calculate the interproton distance. Can get the value of the distance between two spins, or in this case, here it is protons. So what is the distance between two protons? You can calculate from here. So once you know the value, you can calculate that how is the structure of protein or how is the structure of nucleic acid, what are the amino acid residues, what is the distance between them, how it is folded, what is the 3D structure. All these information can be obtained once you know the interproton distance value. So that is to 2D nosy. So it is to a 2D nosy experiment is a very useful technique in structural biology because it helps in the determining the structure of proteins, nucleic acids, carbohydrates, anything. Okay. So that was all for this session. So I hope these questions were clear. Uh, Go through the questions. Try to also go through the lectures. If you have difficulty in understanding any question, then we can take up these questions and again understand them in step by step manner. Okay. So I will end today's session now. Yeah. So thank you for paying attention. and we'll see you again in next session.